Welcome to Unit 8, Video 2, Ionic Compounds. By the end of this video, you should be able to explain what an ionic bond is and how it forms. You should be able to write formulas for compounds given the ions involved. You should be able to identify some properties of ionic compounds. And you should be able to write dissociation equations for ionic compounds in water. Let's start by defining what a bond is. Bonds are something that we've talked a lot about, but we haven't officially defined yet. So a bond is a force that holds two or more atoms together and causes them to act as a unit. A bond is made of a pair of electrons. Now, what happens to those two electrons can vary depending on the type of bond. Either two atoms can share that pair of electrons, or one of those electrons can be transferred from one atom to another. Whether the electrons are shared or transferred determines what kind of bond we have. As we've already discussed, there are two major types of bonds, ionic and covalent. These bonds lie on a continuum. This means that a bond is not either completely ionic or completely covalent. It can be somewhere in between. So looking at this scale on the bottom here, we see at the far right, we have complete transfer of electrons from one atom to another. This results in an ionic bond. And on the far left, we have an equal sharing of electrons. This results in a covalent bond. However, the sharing of electrons can be less and less equal until a complete transfer occurs. So a bond might share its electrons unequally and lie somewhere in the middle of this continuum. We'll talk more about that when we talk about covalent bonds, but for right now it's important to realize that bonds can lie somewhere on a continuum between ionic and covalent, depending on the degree to which the electrons are shared or transferred. Let's focus now on ionic bonds, the subject of this video. An ionic bond is formed between a metal and a nonmetal atom. So anytime you see a compound that contains a metal and a nonmetal, you know you have an ionic compound, held together by an ionic bond. It involves a transfer of electrons from one atom to another. So, when the electrons are transferred from one atom to another, the atom that loses the electron becomes a positive ion. The atom that gains the electron becomes a negative ion. As we know, opposite charges attract, so that positive ion will now attract the negative ion, forming an ionic bond. We've talked a bit about the structure of ionic solids in class. As we discussed, ionic solids will organize themselves so that they maximize the number of positive-negative attractions, meaning that each positive ion will want to surround itself with as many negative ions as possible, and vice versa. Each negative ion will want to surround itself with as many positive ions as possible. Recall that this crystal that we've shown here will continue to get bigger and bigger as we add more ions. Therefore, we refer to the formula unit of NaCl, which is the smallest whole number ratio of ions to each other in this compound. Ionic compounds are very strong and very rigid. Due to this large number of very strong positive-negative attractions, the ions are held very tightly together. Here's another way of looking at this same structure. This is called a ball and stick diagram as opposed to a space-filling diagram. Here again we see that each sodium, represented in this case in red, is surrounded by chlorides on every side. Likewise, each chloride is surrounded by sodiums on every side. Again, if we add more sodiums and more chlorides, this unit cell or this crystal would continue to get bigger in all directions. Basic ionic compounds. As we've said, a formula unit denotes the ratio in which the ions in a compound are combined. For instance, NaCl tells us that for every 1 Na+, we have 1 Cl-. MgCl2, on the other hand, tells us that for every 1 Mg2+, we have 2 Cl-. So what makes NaCl combine in a 1-to-1 ratio and MgCl2 combine in a 1-to-2 ratio? Well, ions will always combine to form a neutral compound. they must combine in a ratio that will cause their charges to balance each other out to form a compound that is overall neutral. Therefore, since sodium has a positive 1 charge and chloride has a negative 1 charge, positive 1 and negative 1 will balance each other out, so they combine in a 1-to-1 ratio. However, Mg2 plus has a 2 positive charge, whereas chloride has a 1 negative charge. So we need 2 negative chlorides to balance out the 2 positive charge on magnesium. When writing ionic compounds, we want to make sure to always write the cation first. Recall that the cation is the positive ion. So for example, sodium chloride would be NaCl. It's a 1-to-1 ratio because sodium is Na plus and chloride is Cl minus, and sodium is our positive ion, so it gets written first. Another example, potassium oxide. Potassium is K plus and oxide is O2 minus. K is our positive ion, so it gets written first, but since we have a 2 negative anion, we need 2 positive potassiums to balance out the 2 negative oxygen, so we get K2O. Here's some examples to try on your own. Pause the video here and make neutral compounds out of each of these. Notice for the 3 at the bottom, you're going to have to first determine the most common ion that each of these elements forms in order to determine what compound you'll get. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice that last one might have been a little bit difficult because the ratio in which they must combine doesn't jump right out at you. Luckily, there's a shortcut. The shortcut's called the crisscross method. In order to use the shortcut, you start by writing the symbol for the anion and the cation, and then you crisscross the absolute values of the charges to give you your subscripts. So Al3 plus and O2 minus will combine in a 2-to-3 ratio. The 2 from the oxygen's charge becomes the subscript for aluminum, and the 3 from the aluminum's charge becomes the subscript for the oxygen. It's crucial that you understand how to arrive at these ratios without the shortcut, but once you get good at it, it's fine to use the shortcut to move along more quickly. Looking now at some properties of ionic compounds, as we said, they're very strong and rigid. This results in very high melting points. Ionic compounds are always solids at room temperature. We've discussed before that ionic compounds can be referred to as salts. Any ionic compound is a type of salt. As you know, table salt, NaCl, is obviously a solid at room temperature, and it takes a very, very high temperature to melt table salt and other ionic compounds. Many ionic compounds are soluble in water. Again, table salt, as you know, is highly soluble in water. As we've also seen, ionic compounds will conduct electricity when they're melted or dissolved. However, solid ionic compounds do not conduct. Recall that an electrolyte is a solution that conducts an electric current. When we melt or dissolve an ionic compound, it's an electrolyte, because the ions are mobile and these charges that are able to move around are able to carry the electrons from one side of the circuit to the other, thereby completing the circuit. Let's look a little bit more closely at what happens when we dissolve an ionic compound. Ionic compounds, when they dissolve, are said to dissociate in water and other polar substances. In other words, they separate from each other. The ions will separate from one another. This happens because water molecules are polar, meaning they have a positive end and a negative end. The negative end of the water molecules will be attracted to the positive ions in the solid, whereas the positive ends of the water molecules will be attracted to the negative ions in the solid. This causes the water molecules to pull apart the ions in the compound. Here we see that the negative ion, represented by the green circle on the right, is surrounded by the positive ends of the water molecules, the little white ends. And the positive ion, the blue circle in the middle, is surrounded by the negative ends, the red ends, of the water molecules. Here's an animation showing this process. Notice the positive sodium ions are represented in white and the negative chloride ions in green. When we put salt into water, as you see here, the positive white ends of the water molecules come in and are attracted to the negative chloride ions and are able to surround it and pull it from the crystal. On the left-hand side, you see negative ends of the water molecules attracted to the positive sodium ion, and they're able to surround it and pull it from the crystal. This continues to happen as each ion gets removed from the crystal and dissolves. Taking a closer look at what happens when we dissolve an ionic solid, here's NaCl. If we put this solid crystal of NaCl in water, it will dissociate. Since it's a 1-to-1 ratio, 1 Na to 1 Cl, we will get an equal number of Na plus ions to Cl minus ions when it dissociates. Notice here there are 5 of each. And again, recall that these ions are mobile, meaning they're moving around in the water, and they're able to conduct an electric current. We can write a dissociation equation as follows. NaCl solid yields, as indicated by the arrow, Na plus ions and Cl minus ions. That's a dissociation equation. AQ means aqueous, for dissolved in water. Here's a crystal of CaCl2. Here, the ions are combined in a 2-to-1 ratio. Therefore, when they dissociate in water, we get 2 chloride ions for every 1 Ca2 plus ion. Notice here there are 3 calcium ions and 6 chloride ions. Therefore, the dissociation equation here would be a bit different. Our solid CaCl2 dissociates into aqueous calcium Ca2+, but it also forms 2 Cl- ions for every 1 calcium 2+ ion. Therefore, our dissociation equation is CaCl2 yields 1 Ca2+ and 2 Cl- ions. Notice the coefficient, or the large number written before each substance, tells us the ratio in which they exist. Finally, looking at an example with a polyatomic ion, here we have Na2CO3, or sodium carbonate. It's a 2-to-1 ratio between sodium and carbonate. Recall the carbonate does not break apart when it's put in water. Only the ions dissociate from one another. So we get 2 carbonate ions and 4 sodium ions. The dissociation equation here would be Na2CO3 solid yields 2 Na pluses plus 1 CO32 minus. Again, the coefficients show us that there's a 2-to-1 ratio between sodium ions and carbonate ions. That brings us to the end of this video. Let's review our goals. First, we looked at what an ionic bond is and how it forms. An ionic bond, recall, involves the transfer of electrons from one atom to another, and then the attraction between the resulting positive and negative ions. Then we learned how to write formulas for compounds given the ions involved. We use the crisscross method as a shortcut in order to balance charges. Then we looked at the properties of ionic compounds. And finally, we looked at how they dissolve in water and how to write dissociation equations for those ionic compounds in water.